So, students, welcome to my class. Smile. Say hi to your seatmate. Now, I'm gonna have a review for a while, but before that, when I say 1, 2, 3, eyes on me, you will say 1, 2, 3, eyes on you. Okay, let's try. 1, 2, 3, eyes on me. Very good. Let's clap our hands. Alright, before we proceed with our main topic, we're going to have first a review. Now, I believe that in our past lesson, we had a lot of things going on. But before that, we're going to count you into groups. So let's start here. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, and 1, 2, 3, 4. It's okay. All ones here, twos, threes, fours. Okay, proceed silently. 1, 2, 3, eyes on me. Again. 1, 2, 3, eyes on me. Very good. Now, I want you to remember your group name. Group 1, where are you? Okay, Group 1, you are the bird. Now, the Group 2, you are the dogs. Then, the Group 3, you are the rooster. Then, the Group 4, you are the cat. So, I want you to remember your group name. Alright, so these are your groups. The moment I present a question, you answer. You answer by group by saying the sound of your group names. The dogs, the bird, the dogs, the rooster, and the cat. So, the moment you shout the sound of your group name, you will be given a chance. You have the chance to answer the given question. So, let's try it. So, our activity will be called as Expand Me. So, let's try it. So, the direction, find the specified term of the expansion in each of the following. So, number 1. What is the second term of 4x minus y to the power of 4? Yes, dogs. Yes, very good. So, the second term is negative 256 x to the power of 3 y. So, next, number 2. What is the fourth term of 5y minus x to the power of 6? Yes, the rooster. Wrong? Yes, you bird. Very good. So, the fourth term is, it's negative. Negative 25,000 x cubed and y cubed. Then number 3. What is the third term of 2y plus 3x to the power of 4? Yes, bird. Bird. Very good. So, the third term is positive 216 x squared and y squared. Number 4. What is the fifth term of y plus 4x to the power of 5? Yes, cat. Very good. So, the fifth term of the y plus 4x to the power of 5 is 1,280x to the power of 4 and y. Then, number 5. What is the fifth term of y plus 4x to the power of 5? Yes, bird. Very good. So, the first term of the 5x plus y is 125x cubed. So, it seems that you have get the our lesson last meeting, the binomial theorem. So, very good. Let's clap our hands. Now, we're done with our activities. So, we will going to proceed to our main topic, which is Euler's theorem. So, what is Euler theorem and who is the proponent of this? So, before that, let us first read our objectives. At the end of the lesson, you, the students, are expected to, first is, know the early life of Leonhard Euler. So, he is the proponent. Next, discuss the Euler's theorem in connection of Fermat's theorem. So, their correlation. Then, prove the given theorem. Apply the Euler's theorem. Appreciate the importance of Euler's theorem. So, Leonhard Euler was born on April 15, 1707 and died on September 18, 1783. So, he was a Swiss mathematician, physicist, astronomer, geographer, logician, and engineer, who founded the studies of the graph theory and topology and made pioneering and influential discoveries in many other branches of mathematics such as analytic number theory, complex analysis, and the infinitesimal calculus. Then, he also introduced much of modern mathematical terminology and notation, including the notation of a mathematical function. And he is also known for his work in mechanics, fluid dynamics, optics, astronomy, and music theory. So, the Euler's theorem, or the proponent of this, Leonhard Euler, he was a Swiss mathematician of the 18th century that made discoveries in mathematics such as the graph theory and calculus. So he also made contribution to things such as the analytical number theory and introduced the notion of mathematical function. So in the category of number theory, Euler developed a theorem called now the Euler's theorem. So, what is Euler's theorem? So, accordingly, Euler's theorem is a generalization of Fermat's little theorem, dealing with powers of integers modulo positive integers. It arises in applications of elementary number theory, including the theoretical underpinning for the RSA crypto system. So, let's move now for the Fermat's little theorem. As stated before, Euler's theorem was made as a generalization of Fermat's little theorem, as I said a while ago, which goes with whenever A and N are co-prime, there are two different forms that are given of Fermat's little theorem. A P is equals to A mod P. A P minus 1 is equals to 1 mod P. This is the foundation of the basis of Euler's theorem. To prove Euler's theorem, one must first prove Fermat's little theorem. So, to prove this theorem, I will be using the formula AP minus 1 is equals to A mod P and using step to prove this. So, next is, the first step is to set P equal to a prime number So a is not an integer that divides into it. So the second step, start by writing the first p minus 1 positive multiples that there are of a, 2a, 3a, 4a, and so on r is equals a p minus 1. So the third step is then take into consideration that both SA and RA are the same modulo P and that R is equals to S mod P. So next is the multiples of P minus 1 of A are both non-zero and distinct. And the fifth step is in order for this to work, the numbers must have some type of congruency to the order 1, 2, 3, 4, and so on, p minus 1. And the sixth step, after multiplying these together, we get a times 2a times 3a times 4a and so on, a times p minus a. Another way that one can look at this is p minus 1 times p minus 1 factorial is equals to p minus 1 factorial mod p. And the last step will be, then one can divide both of the sides by p minus 1 factorial and the proof is completed. So, we are now done proving the Fermat's little theorem. So, let's now proceed to Euler's theorem proof. Once Fermat's little theorem is proved, we can now move on to proving Euler's theorem. Fermat's theorem is known to be a special situation of Euler's theorem as a part where n is a prime number. To go from Fermat's little theorem to Euler's theorem, there is not many changes that need to be made. And here's the formula. AP times n is equals to 1 mod n. So, the first step will be, the first step of proving that this theorem is to consider the numbers of a and n to be co-prime with each other. Then the second step, also, another thing to consider is the set numbers n that are co-prime to the number n. These can be listed as 1, n1, n2, n3, n4, and so on, np times n. So the third step is the set will have the same number of elements as the number of numbers that are co-prime to n. The fourth step, next, take the set that is made of NA and look at it as somewhere where the elements are a product of A and a certain element of N. This can also be written as A, AN1, AN2, AN3, AN4, and so on, ANP times N. Then, the fifth is, the next step would be to look at all the elements that are in the set of NA and consider them to be congruent to an element that is in set N. Mod N, this also shows that the two sets are congruent. Then the sixth step, then one can state that A times AN1 times AN2 times AN3 times AN4 times ANP N is equals to 1 times N1 times N2 times N3 times NPN mod N. Then the seventh step is to take out A, P, N from the equation and divide the second part of the congruent side. Then the eighth, the last one, finally the equation turns out to be APN is equals to 1 mod PN. We are done discussing who is the proponent of Euler's theorem, and we have discussed the Fermat's little theorem and also the Euler's theorem. Now we are going to have an examples the Euler's theorem. So examples using Euler's theorem. Recall that Euler's theorem states that if AM is equals to 1, then APM is congruent to 1 mod M. We will now apply this property to some common question. So the first example is, find the last digit of 55 to the power of 5. So we first note that finding the last digit of 55 to the power of 5 can be obtained by reducing 55 to the power of 5 mod 10, that is evaluating 55 to the power of 5 mod 10. We note that 10, 55 is equals to 5, and hence this pair is not relatively co-prime. However, we know that 55 has a prime power decomposition of 55 is equals to 5 times 11. 11, 10 is equals to 1. Hence, it follows that 11 is not 10 congruent to 1 mod 10. We know that 10 is equals to 4, hence 114 is congruent to 1 mod 10, and more appropriately. So, 55 to the power of 5 is equals to 5 to the power of 5 times 11 to the power of 5 is equals to 5 to the power of 5 times 11 to the power of 4 times 11 is congruent to 5 to the power of 12 times 1 to the power of 4 times 11 is congruent to 34,375 is congruent to 5 mod 10. So, we are going to have the second example so that we can further understand the Euler's theorem. So, another example, find the remainder 29 to the power of 202 when divided by 13. We first note that 29 and 13 is equals to 1. Hence, we can apply Euler's theorem to get that 29 to the power of 13 is congruent to 1 mod 13. Since 13 is prime, it follows that 13 is equals to 12. Hence, 29 to the power of 12 is congruent to 1 mod 13. We can now apply the division algorithm between 202 and 12 as follows. So, 202 is equals to 12 times 16 plus 10. Hence, it follows that 29 to the power of 202 is equals to 29 to the power of 12 to the power of 26 times 29 to the power of 10 is congruent to 1 to the power of 26 times 29 to the power of 10 is congruent to 29 to the power of 10 mod 13. Also, we note that 29 can be reduced to 3 mod 13, and hence 29 to the power of 10 is congruent to 3 to the power of 10 is equals to 59,049 is congruent to 3 mod 13 to the power of 2. Hence, when 29 to the power of 202 is divided by 13, the remainder left over is 3. 1, 2, 3, eyes on me. Students, 1, 2, 3, eyes on me. Very good. So, we are now done discussing the Euler's theorem. We have given an example. Now, we are going to have activity by group. So, the same group, the word the dogs, the rooster, and the cat. So you're going to answer this activity by group. So direction, solve the following using Euler's theorem. Find the last two digits of 3,333 to the power of 4,444. So I will give you 10 minutes to answer, and also after you answer, I will give you 5 minutes to present your output. So you may now start. Okay, time's up. You may now present your output. I will give you 5 minutes each group. Okay, proceed group 1, the bird. Okay, very good. Let's clap our hands. Okay, group 2, the dogs. Okay, very good. Then group 3, the rooster. Okay, very good. Then the last group, the cat. Okay, very good. Thank you for your cooperation, class. Now, we're going to answer the activity so that we could know who get the correct answer. So, the problem is find the last two digits of 3,333 to the power of 4,444. So, here's the answer. We first note that finding the last two digits of 3,333 to the power of 4,444 can be obtained by reducing 3,333 to the power of 4,444 mode 100, since 3,333 and 100 is equals to 1. We can apply this theorem. We first calculate that 100 is equals to 2 to the power of 2 times 5 to the power of 2 is equals to 2 times 5 times 4 is equals to 40. Hence, it follows from Euler's theorem that 3,333 to the power of 40 is congruent to mode 100. Now, let's apply the division algorithm on 4,444 and 40 as follows. 4,444 is equals to 40 times 111 plus 4. Hence, it follows that 3,333 to the power of 4,444 is congruent to 3,333 to the power of 40 to the power of 111 times 3,333 to the power of 4 is congruent to 1 to the power of 111 times 3,333 to the power of 4 mode 100 is congruent to 33 to the power of 4 is equals to 1,185,921 is congruent to 21 mode 100. Hence, the last two digits of 3,333 to the power of 4 to the power of 4,444 are 2 and 1. So class, all of you have the right answer. So let's clap ourselves. So since it seems that you get our lesson now, to further test that you have understand the topic, we're going to have our evaluation. So the evaluation, get one, I think, one whole sheet of paper. So answer this evaluation. Direction, solve the following using the Euler's theorem. So find the remainder of 99 to the power of 9,999,999 when divided by 23. So class, I will give you I think 10 minutes answering the evaluation. So answer quietly. Okay class, time's up. You may now submit your paper. Okay. Okay, thank you. So, we're going to answer the evaluation. So, for you to know that if you have get the correct answer. So, find the remainder of 99 to the power of 9,999,099 when divided by 23. So once again, we know that 99 and 23 is equals to 1. Hence, it follows that 99 times 23 is congruent to 1 mod 23. Once again, since 23 is prime, it goes that 23 is equals to 22 and more appropriately, 9,922 is congruent to 1 mod 23. We will now use the division algorithm between 9,999,099 and 22 to get that. 9,999,099 is equals to 22 times 45,444 plus 11. Hence, it follows that 9,999,099 is equals to 9,922 times 45,444 times 9,911 is congruent to 9,911 is congruent to 711 is equals to 1,977,326 is congruent to 22 mod 23. Hence, the remainder of 99 to the power of 9,999,000 when divided by 23 is 22. Note that we can solve the final congruence a little differently as 9,911 is congruent to 711 is equals to 72 times 5 times 7 is equals to 49 times 5 times 7 is congruent to 35 times 7 is equals to 1,701 is congruent to 22 mod 23. There are many ways to evaluate this sort of congruences, some easier than others. So, we are now done with our activity and the evaluation. So, we'll now proceed to our generalization about the topic. So, overall, there are many different names that are given for Euler's theorem, such as the Fermat-Euler theorem and Euler-Stokes theorem. This theorem is also applied to the basis of the RSA encryption. This was known to be the first practical crypto system that are of the public key and is used all through the transmission of secure data. This is where there is a result of talking a plain text message and encrypting it. Later, this is decrypted. The amounts that are used for the input number by key p n plus 1 for an integer k is positive. This theorem is also applied to this situation as it declares that the decrypted output number is the same value to the number of the original input. which gives back to the plain text. So, Fermat's little theorem became the starting point for the Fermat's primality test. This test is also related to the part of mathematics that most interest me, prime numbers. The primality test is a test of probability that finds out if a number is probable prime or not. Fermat's little theorem is one of the outcomes that comes out of the elementary number theory. This theorem was given its name that included the praised little theorem in order to separate it from Fermat's last theorem that was made. So as one can see, there are many applications for both Euler's theorem and Fermat's little theorem. Personally, I believe that this theorem made by Euler is useful and outside the world of mathematics. Leonhard Euler made important contributions to many different topics in mathematics. His diverse in his studies was known as he was not only a mathematician, but also a physicist, logician, engineer, and also an astronomer. Exploring Euler's theorem has allowed me to draw connection within mathematics, a mathematician, and develop a deeper understanding of many different views of mathematics. So, that would be all the topic about the Euler's theorem. I hope, class, that you gain a lot of knowledge about this theorem. I hope you will you have get many lesson in this topic. So, for your assignment, class, I want you to um, study the binomial theorem for our next activity. So, I hope that you get a lot of knowledge. So, that's could be all. Thank you.